Hello, everyone, and welcome to the stream today. My name is Matthew, and I am one of the staff that works in the astronomy department for Professor Impey, and I help run the classes on online sessions. Thank you so much for being here today. We are happy to see you again. It's only been a little over, I guess it's been almost 2 weeks. But there's going to be a bigger break between the next couple, between the next live session. So thought we'd squeeze one in here. Chris, I'm going to hand this over to you for a moment to welcome everyone, and then I will make our regular announcements and we'll get started with our questions.
Okay, welcome everyone to a live session and Q&As for the online class or however you found us. We'll just get started right away. The floor will be open for any question on astronomy.
Excellent. Thank you very much. For those of you who are just joining us, welcome. Make sure you like and subscribe to our videos. Click the bell icon. That way you'll be notified of upcoming live streams. That's the best way to hear about us. We also have a Google Calendar you can join. We'll start right away with some questions. Supreme Scientist is on with us live and asks, hi, Professor, can you explain how the precession of Earth's axis affects climate on the Earth?
It's an interesting question because the implications of Earth's orbital situation for climate are significant. There are a set of things called the Milankovitch cycles, named after a geophysicist from Serbia, I think, about 100 years ago. And these are cycles that are associated with changes in the Earth's orbit. One is the precession, the 23,500 year precession of one full precession of the spin axis of the Earth, 23.5 degrees offset from north-south. There's another one which is the change in the ellipticity of the Earth's orbit and the obliquity of the Earth's orbit. So these are three cycles, are all in the realm of tens of thousands up to 100,000 years, and they've been implicated in changing climate of the Earth over millions of years. But their signatures are very subtle, and so it is not possible to tease out over a short time span, say since the last ice age, what effects precession of the Earth's spin axis has had on climate. And it's almost guaranteed to be subtle and far less than the human-induced climate change we're experiencing since the Industrial Revolution.
Excellent, thank you. That's a big topic. Next question is from one of our live participants. Let's see, Kendra Smith would like to know, can you talk about when did modern astronomy begin?
That's an interesting question because it's hard to define modern in these terms. Many people, historians of science, would say that modern astronomy began with Galileo because that was the invention of the telescope, and Galileo is someone who many scientists would claim to be the first modern physical scientist because he did experiments, he had theoretical ideas, he understood the primacy of data, and he changed the way science operated in his time. So that would be where many people would say the birth of modern science starts. Perhaps you could go forward to the 20th century and say that modern science starts in the 20th century, and there were certainly revolutions in physics in the 20th century, but I would put the money on Galileo to be the founding of modern science as we understand it.
And then a follow-up question to that one is, would you consider that this means that ancient astronomy was not a true science since they didn't employ today's scientific method?
Yes, ancient astronomy going back thousands of years, of course, it had some scientific elements, but it wasn't fully a science, which is to say it was based on observation rather than just speculating. People actually made observations of phenomena in the sky and tried to replicate those observations. Well, that's a hallmark of science. But what was missing was a sort of theoretical underpinning as we would understand it. People were not able to put forward systematic physical ideas or what we would call testable scientific hypotheses to explain their data. And so while it had some elements of the scientific method, it didn't have enough to be considered truly scientific.
Excellent, thank you. And I think I will then jump ahead to another question that's related, because we're on this nice kind of philosophical discussion about astronomy. LZL would really like to know, can you define or talk about what science is?
Science, in the most general framing of it, is the business of using natural explanations for phenomena. In other words, not supernatural or theistic explanations for phenomena, and trying to explain them using physical laws, essentially. So science does not rely on supernatural explanations. It relies on natural explanations. It's based on observation and replication of data and testing ideas or hypotheses. And so the process of science emerged over a period of centuries. Francis Bacon was a philosopher going back hundreds of years who put in place some of the elements of the scientific method, and they were gradually built over hundreds of years. So I would say during the time from Galileo to Newton, science as an activity took its modern shape.
The next question is from one of our live participants. Paul Michael Johnson asks, with more precise data coming in from the JWST, to your knowledge, do we have any further clarifications or information about the origin of the universe, or for multi-dimensional space, or the nature of the universe?
So James Webb Space Telescope is very successful, and it's impacting a number of fields. It has not made any profound contributions to cosmology yet, and that's the nature of your question, which is the sort of origin of the universe, the nature of the cosmological model. JWST has not contributed to that yet. It might, but at the moment it hasn't. What it's done mostly is do what it was supposed to do, which is move towards detecting first light in the universe, which is to say the oldest galaxies and their properties. And it's found the galaxies grew very quickly, and their embedded black holes also grew very quickly in the first half billion years after the Big Bang. And that's a surprise. It's not a fatal problem for the Big Bang or models of galaxy evolution, but it's definitely stretching our knowledge of how galaxies form to get them assembling that quickly. So as yet, JWST has not tested in a fundamental way the cosmological model.
The next question is from David Gold, who would like to know, how do the theory of general relativity and quantum mechanics conflict or contradict each other?
The two foundational theories of modern physics, quantum mechanics and general relativity, they don't conflict necessarily, and they don't even really complement each other. They're really in different categories. So they're not two things that yet can be combined or reconciled. And that's because they operate in different realms and they have very different conceptual basis. Quantum theory is based on the fact that there's a limit to knowledge and precision of measurement through the Heisenberg uncertainty principle. It also says that the universe on the micro scale is a probabilistic place where we can only assign probabilities to things that happen and not certainty to things that happen. It also says the universe is grainy, fundamentally grainy, where there are finite discrete elements of energy called quanta, and so the universe in those terms, in terms of energy as well as in the units of matter, is discrete and not continuous. That's quantum theory. Now general relativity is rather different. General relativity is a geometric theory of gravity, and it actually is a continuous theory. So it deals with continuous space-time. Mathematically it's called a manifold, which means we describe a curved space-time in purely mathematical terms, but that space-time is continuous, and so it's not discrete and finite and quantized the way quantum theory is. And so they're really fundamentally different conceptions of reality. One, the curvature of space-time caused by mass and energy, and the other, the way matter is organized and the way energy is exchanged in little packets called quanta. The theory that might unite them is a very challenging theory, of course, because each of these two highly successful theories has an enormous amount of development of its mathematical apparatus, and also a huge amount of tested observations that support the theory. So a theory that unites them has a lot to explain, and that sets the bar very high. And at the moment, we do not have a theory that reconciles the two.
Kathy Donnelly have emailed a question. I've seen recent research that suggests the universe may be as much as 26.7 billion years old, which is much older than we thought. Are you familiar with this research? And if so, what are your thoughts?
I'm going to have to punt on this because I don't know the paper it's referring to. It's a little suspicious because that's twice the measured age of the universe from the oldest objects and twice the age inferred from the Big Bang and the expanding universe. So that would be a very radical result if true. So I'll have to look at that. But basically, I'm initially skeptical.
Makes sense. Thank you. The next question is from Sanchita Ghosh, who's on with us live, who asks, what will be the fate of Voyagers 1 and 2? Will they disintegrate into pieces when they run out of fuel?
Voyagers 1 and 2 are in interstellar space. Their energy capacity, batteries, radioactive energy sources are gradually running down and degrading over time, and they will essentially become dead objects floating through interstellar space. Interstellar space is an almost perfect vacuum, though, so these physical objects, these spacecraft, will endure probably for millennia or tens of millennia. There's no reasonable reason they should break apart. The odds of a significant collision enough to destroy them are actually infinitesimally small.
The next question is from an email. Wendy asks, I read that Titan is a super rotator. And I looked that up because I wasn't sure what that meant, but it sounds like it's got a super rotating atmosphere. And so can you talk a little bit about super rotating atmospheres if you are familiar with that and what can cause something like that?
It's usually it's not completely known what causes a super rotation or very violent atmospheric motions. Jupiter has not super rotation, but it has extremely rapid winds. It's much stronger, say, than Saturn, which is a smaller but not vastly smaller planet. These phenomena, these atmospheric phenomena, have to be driven by an energy flow somewhere, and it has to come from, partly of course, from the rotation of the planet. That's the angular momentum, but there's also got to be an extra energy component, which is stirring up a motion or driving a rapid motion. Some of that could be geological heating from the core working its way out through the atmosphere, but this is not a fully understood problem.
Excellent. The next question is from Birhane, who asks, why is it that when matter and antimatter connect, that they explode and create great amounts of energy?
Matter and antimatter are identical entities, except they have an opposite quantum property, and it's the property that relates to the nature of the matter. But it also affects charge too. So the electron has an antiparticle. It's a positron, and the positron has a positive electric charge, whereas the electron is negatively charged. So essentially, all the quantum properties are opposite for antimatter. And what that means is that when these two entities come into contact, there has to be some zeroing out, if you like, of the quantum nature of the particles, and that means they turn into pure energy. When we know this works in the opposite direction too, because it's possible to take pure energy, even the energy of the vacuum, and create particle-antiparticle pairs, and those particles and antiparticles will then just sail off. So from pure gamma rays, you can create electrons and positrons, and that's the process by which antimatter was first detected 100 years ago. So the opposition of the quantum properties is what leads to radiation as the outcome, and it also is what leads to the ability to create equal and opposite particles and antiparticles in energy interactions.
The next question is from Christina, who sent an email. After our sun dies, how much of its mass will be dispersed and how much will be left to form a white dwarf?
The best estimate is that about a third of the sun's mass will be lost in the later stages of evolution, which is to say a red giant phase and a planetary nebula phase, both of which eject outer atmosphere of the sun, a cool outer layer of the sun, and eject it into interstellar space. And so you get left with about 2/3 of the sun's mass, which collapses into the white dwarf, and that's the end state of our sun. And after that, nothing changes. That object just slowly cools forever.
And then kind of a speculative follow-up, would Jupiter be able to accumulate any of that mass enough to ignite as a new star?
No, Jupiter would accumulate some of the mass that was aimed in its direction, but of course it's only going to intercept in a three-dimensional spherical expanding envelope a tiny fraction of that mass, and Jupiter would need an order of magnitude more mass to turn into a star. So even if Jupiter gains a little bit from the envelope of the sun, it will not really change its mass by much, even by much more than 1%, I think.
So you may have addressed this a little bit in the previous question about JWST, but Karen SY, who's on with us live, asks, did JWST's view of galaxies more numerous and larger than expected so soon after the Big Bang surprise you? And what changes in cosmology do you expect as a result?
It was a surprising result to most astronomers, most cosmologists, because we did have theories of how galaxies form from collapsing gas clouds early in the universe, and then how they grow. By dwarf galaxies form first, and then they merge to form larger galaxies. This is called hierarchical structure formation. That idea has been around for 40 or 50 years. So there was a general model of galaxy formation, and that hierarchical structure formation just takes time, because it takes time for the small objects to merge into larger objects. Well, it seems that this process has taken place faster than we anticipated, and it may be a problem for the simple idea of hierarchical structure formation. What's probably the case is that the seeds of the earliest galaxies and black holes must have been larger than we originally thought, and so that would give a kickstart, if you like, to the whole evolution towards bigger and bigger objects. And that will be the interesting thing to discover, whether the very first galaxies, not yet observed by JWST, and the very first black holes are substantially bigger than we expected.
The next question is from a live participant, DSC800. Are there any challenges to the Higgs boson or field theory, or is it taken as fact?
I mean, the Higgs mechanism and the Higgs boson, the discovery from 2012, 2013, has been put in the textbooks at this point. It's the last missing piece of the standard model of particle physics, the entity, the field, basically, pervading space that gives mass to the particles, because otherwise there was no explanation for mass. So that mechanism is understood, but there are still questions remaining, because what's not been seen since the Higgs discovery a decade ago is another set of phenomena that give a deeper understanding of how the Higgs mechanism works. The Higgs should not have been an isolated discovery. There should have been other massive particles in its rough mass range that lead to other phenomena of massive particles and how they interact. And none of those particles have been seen. For example, supersymmetric particles would have been expected and haven't been seen. So the Higgs has tied a bow around the standard model of particle physics, but the standard model of particle physics is incomplete, because it doesn't explain dark matter or dark energy, it doesn't explain the hierarchies of particles, and it doesn't exactly explain the asymmetry between matter and antimatter that originated early in the universe. So the work is not done in high energy physics, for sure.
The next question is from Michael Serrera, who is currently doing dishes and would like to know, do you know how people on the International Space Station deal with common household chores in microgravity?
Yeah, household chores and microgravity are tricky because things just float around and float away. So obviously the worst thing in microgravity is liquids. So liquids are a real nightmare in microgravity, because the liquids there's no surface tension, of course, and there's no gravity to keep them in a container, so they just beat up into tiny little globules, and they just float around and get on things and stick to them and get in the mess, make a mess of electronics and sensitive equipment. So obviously liquids are avoided at all costs. So you're sipping your liquids through a tube from a sealed container and then throwing it away and hoping nothing escapes. But even solids are a problem on the space station. So there's heavy filtration units operating to try and take out small particles. But obviously dust and small particles accumulate because there are people there and they're wearing clothes, and your skin sheds cells, and all sorts of things happen when you're living in space for months and months. So keeping the space station clean is actually quite a big challenge, and it does get dirty over time, and there has been problems with some of the electronics because of that. So it's not a completely solved problem.
The next question is from Bismarck Oliveira, who asks, it seems like black holes in galaxies are always derived from globular clusters, but can black holes occur in isolation too?
Black holes, there are black holes in globular clusters. They tend to be small or intermediate mass black holes, maybe 1,000 to 100,000 times the mass of the sun. And globular clusters, of course, inhabit the halos of galaxies. So these black holes and globular clusters themselves do not explain why you end up with big black holes in the center of galaxies. Those black holes must have formed there right when the galaxy started, and that's the big mass potential well. So globular cluster black holes and galactic center black holes are different beasts, and they probably form in different ways.
The next question is from Pramod, who asks, recently, I've not heard of this being recent, but it was certainly popular in the 50s and 60s, but there was a report of a project to build a fusion-based rocket. Can you talk about promising ideas for propulsion like this that could significantly reduce travel time to or from Mars or elsewhere?
Sure, there have been alternative technologies for space travel. The ideas have been around for quite a while. Remember the rockets that we see around us in the private space program, the Blue Origin and SpaceX, are using chemical-powered rockets. They're just some slightly more sophisticated cousins of the Apollo and Soyuz boosters from the 1950s and 60s, and it hasn't really changed. However, in the 1950s and 60s, there were ideas out there. I think the fusion design you're alluding to in the question was Project Daedalus, came from the British Interplanetary Society, and it was a set of physicists who were working up a fusion reactor-based spacecraft. And so the idea of a fusion or fission-powered spacecraft have been around for a long time. And the issue, of course, is miniaturizing that technology and getting it to work in space. Fission is the most plausible way to go, of course, because we have fission reactors on the Earth, but they're very large, and putting that in space is unfeasible. Fusion would be more efficient still, but is far from being a realistic possibility, given that we can't control fusion for more than a fraction of a second on the Earth. So there are alternative technologies for traveling through space, and they just haven't had a lot of research and development money spent on them in the last few decades. That's changing, but slowly.
The next question is from Hernan, who's not with us today, but sent an email. And the question is about an article that I also saw that claims Beetlejuice, the star Beetlejuice, may have less than 300 years worth of fuel left in its core, and thus predicts the demise will come sooner rather than later. Is this figure of 300 years merely an educated guess, or are there ways of making such a precise prediction?
It's sort of in the middle. It's better than an educated guess, but it is by no means a precise prediction. So if I were going to put an error bar on that 300 years, and I don't know if the paper did, that error bar would be large. It could encompass, 0, of course. It could happen tomorrow, or maybe millennia. So I don't think that's any kind of an accurate number. And the reason is we simply don't measure stellar properties well enough to make that kind of a prediction. Late in a star's life, the evolution is very rapid and nonlinear, and to say where you are in a late stage of a star's life, you have to know the star's physical state very accurately. In particular, you have to know its mass. And Beetlejuice's mass is not known with an accuracy of a few percent or even 10%. and its evolutionary stage is not known that accurately. It's only indirectly inferred from the energy coming off it and spectroscopy of its atmospheric composition. So these are indirect measures. You're not looking into the nuclear core to the physical conditions there. So for those reasons, and the fact that our models of stellar fusion and late stages of stars are also models with imperfections and incompletenesses, then I would say 300 is very much an estimate, a very crude estimate. An interestingly small number, however.
The next question is from Graylight Walker, who's on with us live. Hi, Professor Impey. Do you believe that faster than light travel is actually plausible? And if so, how long till we might achieve it as a society?
Faster than light travel would obviously change everything in terms of space travel or exploring the universe. And that's not just true for us, but true for whoever might have discovered it, if it is possible out there in space. As well as we know current laws of physics, it is not possible. It's not possible because it violates relativity, one of our best held physical theories. Mass and energy are interchangeable, and when you make any object move towards the speed of light, eventually the energy you're trying to put into increasing its speed just goes into increasing its inertial mass, which means it resists any change of its motion, and so doesn't want to be going yet closer to the speed of light. And that's why you can approach but never exceed the speed of light. So faster than light travel would have to violate relativity in some profound way, and so it would be a new physical theory. And maybe people have speculated about what such a theory might look like, but nobody has put a realistic theory on the table. Because again, if you're going to supersede relativity, special relativity, you have to explain everything that special relativity explains and then account for this new phenomena of faster than light travel. And no theory has done that.
Excellent. The next question is from Paul Michael Johnson, who's on with us live. If we were to use something like an Einstein-Rosen bridge or a wormhole to travel a long distance away and then come back, would that be an instantaneous travel, or would there be a distortion in age between those returning or making that trip and those who stayed behind?
It's actually not, there's no simple answer to that, because Einstein-Rosen bridges, the sort of hypothetical wormholes that might connect disparate places in space-time, they can have different structures, internal structures, in this hypothetical sense. We've never observed them. And depending on the internal structure, that dictates how time will operate along an Einstein-Rosen bridge. In general relativity, it's possible to have, within a black hole, for example, a time-like curve, where if you move backwards and forwards along the curve, essentially you're moving forward and backward in time at will. And something like that could happen in an Einstein-Rosen bridge. So you could make time stop or slow down or accelerate depending on how you moved along the time-like curve in this tunnel in space-time. But it's layers of speculation on top of speculation, since we've never observed an Einstein-Rosen bridge or wormhole, never been observed. And the way time would operate in such an object is therefore also speculation, although it is rooted in general relativity. So it is based on a physical theory.
Lorena Castro is on with us live. I have seen some astrophysics conferences in which the constant expansion of the universe is discussed. Can you talk about the latest information or ideas about the expansion of the universe, and how long it will go on and how will it change over time?
The Hubble expansion that was detected just over a century ago by Edwin Hubble, we now know is accelerating, and that's the discovery of from supernovae of dark energy in 1995. So we think that Hubble expansion will continue to accelerate as much as we know about dark energy, and that's not a lot. That expansion rate will just continue to increase. And so the universe and space-time will just be sort of pulling itself apart over the future of cosmic time. There's no indication that process will reverse unless dark energy it has some decay component or is evanescent in some way and is not stable long term, and then all bets are off. But at the moment it looks like accelerating expansion forever.
The next question is from Underpass 79. How do you make the connection between general relativity and the Higgs boson, say time stands still in energy, does the type of time of matter also begin at the moment when energy transforms into matter?
So general relativity does not formally connect to the Higgs mechanism. That's the simplest way of putting it. General relativity is looking at the curvature of space-time, which relates to the presence of mass and energy in that space-time. The Higgs mechanism is what attributes mass to subatomic particles. So you really have a quite separate mechanism going on there. And it's true that subatomic particles are going to have an effect on space-time, but of course it's a tiny effect because space-time is really only perceptibly altered by massive objects. So they're really in completely different physical realms, and there's no simple way to connect them theoretically.
The next question is from one of our live participants. How does the Big Bang explain celestial dynamics and sources of motion?
So the Big Bang is a overall event that ascribes to initial starting point and possibly a cusp or an infinite density and temperature state, the expansion that then follows. Now that expansion is uniform, the Big Bang itself actually doesn't explain celestial dynamics, doesn't explain all the detailed motions of objects in the universe. It just provides a backdrop situation where space-time is expanding, and then the objects within that have different behaviors. So all that it is sort of like the wallpaper. It's like the canvas for the universe expanding. All the motions of the objects within the universe depend on gravity and how those objects form. And as galaxies collapse and stars are formed within galaxies, they all have their motions. Motions are imputed by external forces, by interactions with other galaxies, turbulent motions, and so on. So the complexity of stellar dynamics all happens on smaller scales and after the Big Bang, and is really not associated with the theory at all. It's due to all sorts of gravitational influences and interactions and perturbations operating over billions of years.
Francisco Estrada, who's on with us live, asks, what do you think about the controversy over ground-based astronomy and Starlink launches? What is the state of the art in this problem today, and how do you think it can be regulated for coexistence?
So the Starlink constellations of satellites are growing in number. The number of satellites in low Earth orbit has been doubling every 5 years or so, and is going to double again several times, and may end up at about 30 to 35,000 satellites in 5 or 6 years. That's an enormous number of satellites. The problem with these satellites is they're in low Earth orbit, so they're close to the Earth. When the sun is low on the horizon, either horizon, they reflect sunlight down to the Earth, and so in twilight observations, astronomers see streaks of reflected sunlight from the Starlink satellites as they move across the sky. And because they're fairly close to the Earth, those streaks are pretty bright. These are visible to the naked eye, in fact, sometimes. And it's a problem for astronomy. And it's a problem because the number of these satellites is still growing rapidly. They were designed by SpaceX and other companies to deliver wireless internet to places on the Earth that don't have it, and that's an admirable goal. They have a profit motive, of course, too. They're not just giving internet to Africa for free. However, for astronomy, it's bad news because there's already signs that the number of star trails on Hubble Space Telescope images has increased from a few percent 10 or 15 years ago to 15 or 20%. In other words, the odds that a deep Hubble image will have a star trail on it are getting significant. For future telescopes, like the Vera Rubin Observatory, which will be surveying the whole southern sky to Hubble depth every few days, the odds are that many of its images will be affected by these trails. There are digital methods to filter out the trails, but you lose a lot of data by doing that. They create a big ugly streak across the image, and there's a lot of these things. Mitigation is tricky. It's not entirely confrontational. SpaceX has been in conversations with the International Astronomical Union, the American Astronomical Society. They've already changed the nature of the coatings that they put on these Starlink satellites to make them less reflective. They also leak radio emission. That was a discovery from the last few months. Radio astronomers have seen are getting interference now on their sensitive radio observations in protected radio bands from Starlink satellites, and hopefully they will work with radio astronomers to mitigate that too. So the two parties are dialoguing. I don't think SpaceX wants to make enemies of astronomers, and they don't want to mess up the sky, but they have pretty big ambitions, and so I think the problem is going to get worse before it gets any better.
The next question is from an email. How do gravitational waves affect the residual cosmic microwave background, if at all?
Gravitational waves, because they're perturbations or disturbances in space-time, they affect the microwave background because the microwaves are traveling through space-time. And so gravitational waves can create an anisotropy, which is to say sort of a change in the directionality of microwave background radiation as the gravitational waves flex space-time caused by some signal from some event in distant universe. These are very subtle effects, and microwave background observations are not sufficiently good to tease them out. There's hope, perhaps, however, since microwave backgrounds are also diagnosing early universe physics, that in some of the more dramatic physics of the early universe, where the gravitational wave signatures are pretty noisy or stochastic, or mostly random signals as opposed to periodic signals or in-spiral signals of black holes, that there will be a real effect of this gravitational wave background on the microwaves that we can observe with radio telescopes. That's a hope, but we don't know how that'll work yet.
The next question is, it's somewhat specific, so feel free to move on to the next question. But Rentgen 101 would like to know if you have heard of the recent observations of a star swallowing up a planet, and if you can talk a little bit about how that, that detection, I guess they used some spectral observations to make this detection, what that means.
Yeah, there have been a couple of these, actually in the last few years. There have been a couple, one in the news a few months ago. It is certainly true that soon after planets form, they are still sitting there with the material that formed them, so that material does not disperse for a while after planets form around a young star. And of course that material then exerts a drag on the newly formed planet, which causes it to spiral towards the star. And so we think in the process of forming giant planets, many Jupiters and Saturns are engulfed and swallowed by their stars early on. It's hard to see evidence of this happening. So we've started to see evidence of situations where stars do consume the planets around them. These planets are obviously in very close, rapid orbits, and they probably are in a young situation where there's a lot of gas still in the system, which creates drag, which causes them to spiral in.
The next question is from is from an email. Taurus asks, I'd like to know why we can't measure the exact distance to Beetlejuice, even though we know the distance to much more distant objects like the M13 globular cluster.
Right. To a single star, to measure distance is tricky. If it's too far away to measure a parallax angle, that's a geometric distance, and that is the case with Beetlejuice. It's just too far to do that. I don't even think Gaia can do that, the new satellite the Europeans are working with. So without parallax, you're left with indirect methods. You actually have to have some diagnostic of the star to tell you its mass or its physical size. And Beetlejuice is resolved. I mean, it's a large enough star that its angular extent has actually been measured with telescopes, but not very accurately because it's still a star and it's hundreds, thousands of trillions of miles away. So the simple answer is that we don't measure stellar quantities of individual isolated stars accurately enough to measure their distances with any accuracy. The
next question is from Faisal, who asks, the Earth, the Sun, most of the planets, as well as the other solar systems in the Milky Way, all seem to rotate counterclockwise. Does that apply to all galaxies, and is there an explanation for it?
There, overall, on the largest scales, there should not be any net trend in the vector of angular momentum. In other words, people have looked for patterns of galaxies and have looked for the fact that their angular momentum vectors could be aligned. And there have been small effects perhaps found, but there's no large-scale effect. In other words, on the largest scales of the universe, things rotate in different and randomly different directions. And that makes sense because there would have to be some overall net angular momentum vector of the entire universe for that not to be the case. And these varying angular momentum vectors probably reflect turbulence, and turbulence is a chaotic process whereby you form eddies in gas and circulating liquids, and these eddies have random orientations. And so there should be no alignment of large-scale rotations in the universe, and we don't really see any.
The next question is from Junior World, who's on with us live. Hi, Professor. My question is, science says that energy can neither be created nor destroyed. Then how could energy come into existence for the first time?
Well, that's a good question. So how could the universe come into existence, let alone the energy and the mass? Energy can't be created or destroyed with one exception, and that is vacuum energy. So we know that the vacuum of space, pure vacuum in a lab or in deep space, does not contain nothing. It contains a half of a Planck constant's worth of energy, a very small 0-point energy that is measurable in the lab and creates physical effects. You can also borrow energy from the vacuum as long as you pay it back sufficiently quickly. That's one way of expressing the Heisenberg uncertainty principle. So there are mechanisms whereby there is energy in the vacuum of empty space, and other mechanisms, well known in physics, for borrowing energy and converting it into mass, as long as that gets returned eventually. So that doesn't necessarily explain the universe, because the universe would be, as Alan Guth said, the architect of the theory of inflation, the ultimate free lunch. And he's alluding to the fact that you can get enormous amounts of energy out of the vacuum if you get that energy very quickly.
We have two questions about exoplanets, so we'll do them in particular order. So Dave McKenzie's email says, with telescope technology advancing, how far off are we from nailing down or knowing for sure that an exoplanet is truly Earth-like?
We're pretty close. There are Earth-like exoplanets at the level of 20 to 30% difference from the Earth in terms of mass, in terms of size, and in terms of orbital parameters around the Sun-like star. So that's pretty close. I think the goal of finding a true Earth clone is almost a misleading or mistaken goal. It's not necessarily a good goal, because we don't know that the Earth is the best of all possible worlds in terms of habitability and hosting life. So there's no particular reason to search for a complete twin of our planet. Almost certainly and statistically, it must exist. If you look hard enough and far enough, we would find something that was very Earth-like as we could measure. But I think astrobiologists are taking a broader view of this, and they're really interested in habitability of planets. And they've decided, for example, that super-Earths, that's planets 1 or 2 times the mass or size of the Earth and 4 to 6 times its mass, might be just as habitable as the Earth. So in terms of looking for life in the universe, maybe we shouldn't focus exclusively on Earth clones.
Lee Bergen then asks, what kind of life would astrobiologists expect to find on a planet with Earth-like conditions, except maybe higher gravity, so a slightly larger mass?
So if the chemical conditions were the same and the energy conditions in terms of the star, then it's not clear how life would evolve. We can imagine there's a universal biochemistry. That's an argument that's been made decades ago. And so that carbon-based life would happen and there would be some replicating molecule. But we can't even be sure that the first molecule that codes information in biology is going to be RNA or DNA. It might be something quite different. Or you might have a situation where a complex web of metabolisms evolve without the large coding molecule of RNA or DNA, and that might have happened on the Earth too. So we're so uncertain as to how life progresses that I don't think we can answer this question, basically.
David Gold would like to know, who are some authors that you know of who have tried to harmonize the mysteries of cosmology and theology?
Well, there are people who've made an interesting study of this. I mean, there are people who've written from the perspective of theology about cosmology. I'm having trouble thinking of one at the moment. I mean, there's a colleague of mine, Bill Steger. He died 5 or 6 years ago. He's a cosmologist and he's a Jesuit astronomer, and he's written about theology and cosmology in his work. But there are people who are trying to reconcile these things. Sorry, I'm coming up dry with some names here on the cuff.
I totally understand, and as you think of them, feel free to bring those up. The next question is, can you talk a little bit about what you know about ancient Indian mathematicians or astronomers and how they have contributed to modern astronomy?
India was a very important player in mathematics and astronomy going back 2,000 years. And so the Hindu tradition definitely has strong mathematics. It was also mixed with the tradition in Islam, where a lot of innovations in number systems and in optics were made by Islamic astronomers. And there was commonality. These cultures talked to each other. They were adjacent in Asia, and they talked to each other. So Indian astronomers have made great observatories going back 400 or 500 years. I visited a couple of them in the north of India. These are not modern observatories in the sense of optical telescopes. These are telescopes, observatories of the kind that Tycho Brahe made when he measured the motions of Mars. So these observations were important, and I think astronomy was important in the sort of hierarchy of the powers of ancient India. But they were not making scientific discoveries at this level, because this was, again, in the pre-scientific age.
The next question is from Christina V., who sent an email and would like to know, she says, Jupiter and Io generate 2 terawatts of electricity between themselves. How is that, can you just talk about how that energy is generated, and if you know that, is that quantity, large, small, in
there's a
grand
large
scheme of
amount
things?
of energy, and it stems from two things. It stems from the fact that Jupiter, of course, is a massive planet, has a very strong magnetic field, and it stems from the fact that Io has what's called an ion torus. So Io, moving through Jupiter's magnetic field, creates a torus, a very diffuse plasma torus that's ionized material. And so you can get a sort of dynamo effect here. When you mix electrical conductivity from an ion plasma with a magnetic field, you can generate an electrical current, electrical charge. And so that's where that large number comes from. And it comes from mostly the large mass of the planet Jupiter.
Excellent, thank you very much. The next question is from Eliezer, who would like to know, do you think that there might be a possibility of another large planet being discovered in our own solar system?
The odds of a new planet being discovered in our solar system are really small. I mean, there's no room for a planet in the inner solar system. And this is a theoretical constraint, too. If you people have done this in simulations of our solar system in computers. If you drop a planet like the size of Mercury anywhere in the inner solar system, say between Mars and the Earth or between the Earth and Venus, you would disrupt on very short orbital timescales the orbits of the inner planets and eject some from the system. So the solar system will become violently unstable. And so that pretty much says that the solar system is dynamically full. There's no room for any other planets. So therefore, it's almost certain that we found everything. once you get to the outer solar system, and especially to the Kuiper belt, then it's a lot less clear, because there are obviously Pluto-sized objects or dwarf planets in the Kuiper belt. The Kuiper belt extends from 40 to 80 astronomical units, and it has a large number of objects that are the size of large asteroids or small planets or large moons, and we're discovering them slowly. But there is no missing planet within the realm from Uranus and Neptune into Mercury.
The next question is from email. Ganymede and Europa both have been found to have very thin atmospheres of O2, or of oxygen. Do you know if there's any connection to them having liquid oceans beneath their surface?
Yes, the fact that there's a diffuse oxygen atmosphere on worlds that have subsurface oceans, as both Ganymede and Europa do, and in Europa the case is proven that there's a subsurface ocean, although we've never seen it directly from underneath. Ganymede also is likely to have a subsurface ocean, and it's a much larger moon. As soon as you have these systems with active geology, where the active geology is partially boosted by tidal heating from the parent planet, then you have means by which you can create oxygen ions, and the ions can seep through the crust, the Earth, this crust, the rocky and icy crust, and become a very diffuse atmosphere. So there's mechanisms of energy to create oxygen ions from the water itself, or from the carbonates or silicates, the rock itself, and then that will seep through the crust very slowly to form a very diffuse atmosphere.
The next question is from Lawrence K, who asks, if the universe is accelerating, will the expansion ultimately reach or exceed the speed of light?
Yes, if you pick the correct scale, even in the universe we measure right now, then that must be the case. And so if you extrapolate an accelerating expansion, you definitely reach the position where 2 points in space-time are moving faster than light speed away from each other. And that means the information becomes acausal. In other words, we're not going to see information from those regions that are expanding faster than light speed away from us. And there could be a very large amount of space-time that's in that category. In other words, the observable universe in an accelerating expansion could be a very small fraction of the entire physical universe, because so much of it is beyond our light horizon, or a horizon where we can get signals reaching us due to limitations of light speed.
The next question is from Frederick Sherman, who asks, has time always existed, or did it start at the Big Bang?
In this conventional understanding of the Big Bang model, time did not pre-exist. Time as we understand it did not pre-exist the Big Bang. Time is a function of our expanding space-time, and the forward flow of time is partly due to a dynamical process whereby the universe evolves and changes its properties in a systematic way. So the Big Bang really does correspond to time equals 0, and there's no conception of time before that point.
The next question is from an email. If Beetlejuice were to explode shortly, what would happen to Earth? Will the aftershock reach us in around 600 light years, because that's how far away it is from us? Would it reach us much later?
Well, if we see, of course, the irony is if we see Beetlejuice explode, then the information is reaching us right then, okay? That means the event happened centuries before. We're trying to predict what's going to happen in the future. If Beetlejuice did explode, it is far enough away. It's not one of the nearest stars by any means. There are thousands and thousands of stars closer. And even though it's a big star and it would create a violent explosion, it's not going to have any significant problem for the Earth. Supernova has to go off within 20 light years, roughly 15 light years of the Earth, to cause substantial problems for the Earth. So Beetlejuice would be a very spectacular light show, but not anything fatal to our planet.
Paul Michael Johnson would like to know how many ET, extraterrestrial cultures, would you guess are on our planet right now in a range from 0 to, say, 30?
I would guess 0 because I would want to see evidence of them. So there's a lot of ideas out there. There's a lot of supposition that aliens have visited. There's obviously a realm of conspiracy theories around that kind of thing. But scientists have a pretty high bar on evidence to support that kind of hypothesis. And despite all the speculation, despite all the stuff you read online, hard physical evidence is that any astronomer or any scientist can inspect and at their will and then pass the communicate that on and publish it is completely lacking. So I put that number at 0.
Excellent. Well, it is 10:58. I think we're going to take one more question and then wrap it up for today. So we've talked a little bit about faster than light travel. Can you address specifically the idea of warp drives? Is something like that possible, and might it be able to help us travel faster than light?
Warp drives are fictional concepts, basically. They're used in science fiction and Star Trek and other science fiction vehicles to make vehicles move very quickly through the universe because space is big and it takes a very long time to get anywhere. There was a fuss in the literature for some years about what's called an Alcubierre drive. That's the name of an astrophysicist who proposed a mechanism whereby you essentially could set up a space-time wake and somehow propel something faster than light speed. People have looked at that idea fairly carefully, and the jury is not in yet because it's an interesting idea and the physics behind it is definitely real physics. But nobody thinks there's an actual mechanism where you could create this effect, this physical effect in space-time that Alcubierre has written about. That's the only research level idea that's been in the literature, that's been commented on by scientists and theorists. Otherwise, warp drive is definitely just a fictional concept. And it does violate energy principles and relativity, so that's a big mark against it, even in principle. Thanks for all the questions. Good questions this week, as always. And thanks to Matthew for facilitating. And we do have one more on the books. I have a trip in a week or so to Ecuador. There's an international astrobiology meeting, so I'll be away for a while.
Excellent. Thank you all for joining us. The next session will be Monday, August 14th. So that's a few weeks away, 3.5 weeks away from now. So we hope that you all have a nice break and join us back here for that. Again, if you just joined us, make sure that you like and subscribe the channel and click the bell icon because we have to, that way you'll hear about our upcoming live sessions. So thank you all for joining us, and we will see you in a few weeks. Take care, everyone.